like you're just going to say ME equals U of X plus KE, right? And then you're given everything, just plug it in. Okay. Any questions on that one? We're good. Okay, I don't even think I need to do that one. Then B, calculate the X coordinate of any points at which the object has 0 kinetic energy. So if you have 0 kinetic energy, then that just means the ME, whatever you got up here for ME, is going to equal the UX. So that means your ME is going to equal your 4x squared. So x is going to be the square root of ME over 4. Pretty straightforward there, too. Okay. Then calculate the magnitude and momentum of the object. So for this one, okay, at that point, we can say, once again, ME equals U of X plus KE. So then we know ME, it's a specific value. I don't know what it is, but just get it up here. And then U of X is 4 times X squared, and then this is 1/2 MV squared. Okay, so we can solve for V, so whatever, that becomes 2, that becomes 8. V is the square root of 2ME minus 8x squared over M. Once you do this, just multiply this by M and you're good. That's your momentum. So those are all straightforward. Like, hard to believe that that's even on an AP physics test. Because you should be like, even if you took regular physics, you should be able to do this. Then for D, calculate the magnitude of acceleration. So for this one, acceleration we know is related to force, right? F equals ma. So then, if I have no idea what to do, I look at my formula sheet, and what do I discover? True, that's there.
And also B equals B0 squared plus S28x minus x minus the initial distance from.
Well, let's think a little bit more in terms of what they're asking and what we have. So they want an acceleration, okay? And the reason I went F equals ma is because the things that we're talking about here is energy, right? So how does acceleration relate to energy? We know that acceleration is force, and then force times distance is energy. Yes? Right. So is there an equation from your formula sheet that talks about force and energy? Unless it's from your book. The basic kinematics equation.
You could use.
So if you could solve for the velocity at that point.
No, you already have the velocity at the.
Oh yeah, so we already have that here.
Yeah, and then you can just use V0
And then
squared.
we know the points at which it's 0. Does that work? Is it the 9 plus that? Oh, what is it? What is it? Yeah, the F dot dr. If or force times dr. It's not a dot. Now that dot means something different. Well, I guess that is dot. But anyways. Yeah, if this is energy and this is force, right? So like you can use that relationship. There's actually something in the book that says this. And this is actually, oh gosh, what is this? Chapter on work and energy, like chapter, whoops, my book is falling apart.
In the book, Voltaire's opinion.
Voltaire's kind of
Why in the world would syphilis be the best of both worlds?
Voltaire.
Voltaire says.
Very satirical.
Oh, okay, so he's making fun of it.
Yeah. I like him though. He's really like. I think it's like our last.
What is this?
I don't like the way he dies.
Yeah. You should. You should.
It was creepy, but then I don't like how he dies and then the apple on his back. Then he like lets himself die, but then like the apple on his back and walks him off his
Sort of like a tree. That book fell apart. That sucks.
At least the pages are in order.
I know, right? Okay, I'm just gonna leave the book there. All right. Oh, what's this? Okay. So I'm curious, Dave. What kinematics did you use? So we know the velocity at this point because we solved it here. We know the x coordinates. So we know the x coordinate here. So we know v. We know x. And I guess you could say we know initial velocity. You mean this one?
Yeah, the initial velocity has to be 0. But I assume that the object didn't move prior. So like as it passes 0.6, like.
Well, see, if you say that you assume that the object's not moving, you have to use one of these points, right? Because like here we're solving the points at which the object has 0 kinetic energy. Is everyone aware? Well, okay, let me see this. Is everyone aware of what's going on here? Right? This object, like if we do an energy sort of thing, an energy versus I don't know, like if we do an energy versus position, right? Like it goes, that equation is something like this, right?
Yeah.
So then the energy goes back and forth, yes? Because we know that there's a max of, what is it, 7 joules or something? There's a max of 7 joules. So then it just oscillates back and forth between those two positions, wherever these two extremes are. So the points at which the kinetic energy is 0 and therefore has 0 velocity are here and here, right? Which comes out, what is it? That's 1.5? Is that what it was? I don't know. Some x and some negative x. So if we're saying this is at point, right, like right here, 0.6 meters. So you said from 0, right? What did you get the right answer yet? Interesting. Okay, well let's just walk down that path. So we know this x, we know the v from there. What else did you? And then you used.
I said
v0 is 0.
Yeah. Like I was surprised I got the right answer. I just wanted to try it out.
And so did you use what, like v squared is equal to v0 squared plus 2ax?
Yeah.
There were time music. You just said it as starts off from like position 0.
Okay. So then this, yeah. Okay, let me see. Is there anything that indicates? Because then this operates under the assumption that a is constant, that the force exerted is constant throughout the whole thing. Interesting. I didn't even think about doing that. I wonder, did you check the grading thing? Did it say that you could do that? Like it's an alternate or something?
Bobby's told to use a force code, like the word to use it or use like
Okay, well, that's interesting. I mean, do you see what I mean about like this equation, these basic kinematic equations, operate under the dependence that A is constant. So this force has to be the same through the whole way. Luckily, in this case, it is. So that's why this works. Okay, well, that's cool. All right. Well, anyways, are there questions on B? So Dave did it by just using the kinematics equations, and then because, like the kinematics equations, the important part about them is you have to remember they're only for when acceleration is constant. So when the acceleration changes, that's like a new part of the problem. So you have to be aware of that. If you have an acceleration that's constant throughout the whole thing, then boom, knock yourself out.
So maybe that's how we distribute use kinematics in this. Or do they just
Well, let me see what they said.
you have intervals? If you do the F equals MA, like you have intervals. Like a zero function. And you're plugging values in. I don't know. So basically you have work is equal to interval of work is equal to potential energy. Because work is technically it's in joules, which is
Really?
someone
Hopefully not in here.
Well, not here, but like over the past like 4 years.
Okay, so between force and potential energy. Interesting. So they use this right off the bat. And where'd you get that? That's not on your formula sheet. It's on the book. I think the book talks about it. In one of the chapters, I think we had a problem like this before. Actually, I think we did this problem before.
yeah, I think it is.
So this is their alternate solution there. They didn't use kinematics, they used energy. Or did they? No, because then they took the derivative. No, they didn't. They made a differential equation. That's interesting. I would say my guess would be if you give a reasoning as to why you believe that the potential energy, the force applied by whatever this thing is, a rubber band or a spring or whatever, that is constant. If you could show that, then you could do that. You could get away with it. Because that only works because A is constant. Is A constant? Yeah. Yeah. Got it. I'm sorry, what's that? Shh, please. I can't hear. Yeah. Oh, so you're saying like kind of assume like it's a spring, and then which you could almost calculate K by using the potential energy, right? Saying this is equal to 1/2 kx squared. Interesting. Yeah, so I guess the issue is that you have to do something to say that the acceleration is constant. So yeah, maybe you could, like I said, you could do some sort of an energy thing, and then try to connect this to potential energy of the spring? That's possible. Okay. Yeah, the way the author does it is just through the relationship between force and energy. Okay, so if we continue on then, down below to the graph. Okay, so here for the two graphs, the kinetic energy one is pretty obvious, right? Because there's this maximum amount of 7 joules. Like the kinetic energy can't be any more than that. And remember we already did this graph, where this is the energy and this is the displacement. So you can see here, right, that it's the potential energy is 7 joules at these 2 points. Right? Those are the points where if this potential energy is, then the kinetic energy is 0. And then at this point, we know that the potential energy is 0, which means the kinetic energy must be maximum. Does that make sense? So then you can say at this point, right, at 0 x, then 4x squared becomes 0. So there's no potential energy at 0, which means this should start up here. Right? And then it's going to go as this goes up, right, to its maximum position of displacement, which is at 1.3 meters. Then the kinetic energy will go to 0. So it's going to come down to 0 like this. And then when it comes back, because the V is squared in the kinetic energy, that's never going to, it's never going to be negative. Right? So you can't make this negative. Give you some like whatever like this. Right. So do we see how that works here? And then this is the displacement versus time. So hopefully you see from this, we start off, it just depends on how we start off. If you start off like this, then this should start off at 0. And then it goes to some position, and then it goes like this. And actually, I should be more careful, because let's make sure that we're okay with this, because this point and this point, those have to be zeros. What's that?
Oh,
Yeah, they have to be connected. Right? So, because whenever kinetic energy is 0, that's at one of these maximum displacements. Right? So this maximum displacement is there, and this maximum displacement is there. So it's like this. That's terrible, but you get it.
Wait, so why is the second one all the way?
Wait, this was 0. 0 kinetic energy. Did I graphed this right? Because at the bottom it has maximum, right? Yes, if we start there, it has maximum and goes up. So this, so this also has to be a place, because the kinetic energy is maximum when the displacement is 0. And then when the displacement is maximum, I'm screwing up the graphs. This is the potential energy. Okay, potential energy is 0. What kinetic energy is 0? Okay, cool. So if we go there, maximum displacement is when kinetic energy is 0. Maximum displacement is when kinetic energy is 0. So yeah, these are the 0 points. So yeah, it's like this. There you go. That's better. Sorry, I kind of hit myself, but yeah, that's how it works. And then so here, when kinetic energy is 0, that's where it stops before it turns back, and that's at the maximum displacement. And one of those maximum displacements at 1.3 meters. One of them is at negative 1.3 meters. Yeah.
So how about the potential energy graph looks like that, while it's like kinetic energy graph looks like that?
Well, this is the energy. This is the potential. Oh, sorry. This is U of x, right? The graph of U of x.
Yeah.
This is x versus t, and then this is k versus t.
And K versus T has
Yeah.
a smaller period than U versus T.
Yeah, because okay, so if we look at what's happening here, right? This is Ke max, and this is KE0, right? And when KE is max, that means it's 7 joules, right? And that means there's no potential energy. And where is potential energy 0? It's at the 0 point, right? It's at the 0 point. So we know that x value, which is up and down, that the potential energy is 0 at x equals 0. Does that make sense? Okay. So then we know whenever KE is max, then x has to be 0. Okay. So then the other thing is down here, each one of these, here and here, is KE equals 0. And when the K equals 0, then that means the potential energy must be max, right? And if the potential energy is max, that means you must be maximally displaced. So wherever, if I do this with a different color, wherever the bottom is, that's wherever the nadir is on this, that should be a max here, a max displacement, and that's the way it works. Now they're not drawn correctly, so they're a little bit out of scale, but.
Oh, so in other words, in reality, like the KE is probably just like it's basically the same equation. Like it will look exactly the same as the other graph is shifted.
No, well, this goes through 1 lambda when this only goes through lambda over 2.
Oh.
So yeah, it is this. That's the way. Yeah. Questions? Yeah.
I guess I might disagree. Why for the case you decided to
I know this a little bit. Well, because I wanted to go through the whole thing, like the whole cycle.
Whole period?
Oh, yeah, they said it was conservative.
Yeah.
In a real life situation, yeah, like the kinetic energy would have a graph, like it would be a slope going down like this. Yeah, but if you say it's conservative, then it's all like that. Any questions? Yeah. Sure. Okay, so we don't know what's going on. All we know is we're given an equation that describes the amount of potential energy in the system. Okay? And so we're also given a specific amount of kinetic energy, or we're given a specific velocity at a specific position. That allows us to kind of nail 2 things down. Number one, I can draw the graph. And from the graph, I'm like, okay, cool. I know the general thing, right? That if we start at infinity, then this thing's going to go on and go like that. But because I'm given a specific velocity and a specific rotation, that locks in the fact that I have a maximum in my energy. You know what I'm saying? So there is a max limit in the energy of this curve. Because without that position and velocity, we know nothing. Right? It could be infinitely anywhere we want to go on this. Now the curve stays in the same shape, it doesn't change. But it's just massive. We don't know what happens. But because we know that there's a specific velocity, now we can say there's a total mechanical energy. And it can't go past that mechanical energy. So then we can draw that dotted line across the top, up there, on the potential energy versus position graph. And then now we can say, aha, I know that this is going to oscillate. I guess you could argue that, well, are you saying like, does it only do it once? Oh, because it still has energy, right? Like, where is that potential energy from? Okay, so if we just saw that graph with no limit, we wouldn't know it. Then we know that there's a value for kinetic energy. So then that means this system operates by, as it loses kinetic energy, or sorry, as it loses potential energy, it's gaining kinetic energy. So there are 2 forms of energy in the system. If a system had potential and kinetic, like, for example, rolling down a hill or something, and that there was like Yeah, you don't know what happens. Like, without that, you might be able to say, oh, well, here it has this velocity. Oh, yeah, okay. Because it has potential energy in both positive and negative, like something like how would you move in a normal system with potential energy on both sides, right? Like if you just think about it, if you walk through it in terms of just saying it, okay, I have a big amount of potential energy here, and then as I move towards that, towards x equals 0, my potential energy goes away. And then as I go to the other side, my potential energy starts to build up again. Right? That kind of communicates that it's like an oscillating spring system. So we know this is either a spring or it's like in a bowl, going back and forth, or it's some sort of gravitational oscillation.
We only know it oscillates because of the equation.
Yeah, like what? Yeah, the Forest Spur gives us a parabola.
Yeah. Well, then that is actually is that how you find out whether it's oscillating? Do the function.
Oh, you know what this is taking, like, okay. The trick here is going from like energy versus x to energy versus time. Okay. So how would you switch from energy as a function of time? Energy as a function of space and energy. I think the nature of this problem, they just want you to say, oh, that's a spring. Because how the energy plays itself out. The farther it is away from the center, the more force it gives. You could also look at if force is the negative derivative of position as a function or of energy as a function of space, then that means when you take the derivative of acceleration that comes back from the middle. Do you see that? Yeah, if you take the derivative of this, right? When you get like the negative derivative of 4x minus negative 8x, right? And then that negative 8x is the force that's being applied to the system. Yeah, this force is a good system. Does that work? Even if you just got lucky. No, I'm serious. I think they specifically picked that point because by picking that point, you will get to the right answer. But then it's not going to be equal. Because this system doesn't have a constant acceleration. Yeah. So that doesn't. Hey, did you hear that, Wayne? This system, okay. So this system doesn't have a constant acceleration. Its acceleration is because if from the book, like in the book, it's when it talks about a force and springs, it talks about the force being the negative derivative of the potential energy as a function of displacement. So F is negative du dx, right? And du of x over du. Yeah. So when you look at the derivative of the energy as a function of displacement, then you see that force, when you take the derivative, you get negative 8x, right? So then if you get negative 8x, that shows that acceleration is not constant. Acceleration is a function of displacement. So because of that, you can't use the kinematics equation. But that's how you know it's going back and forth. Because when it's over there, acceleration is positive. And it's over here, the acceleration is negative. So that is without a doubt the answer. I didn't think
Wait, so how do you solve it using force? If kinematic
you take, well, okay, since you know force is the negative derivative of the energy function, then you just take the negative derivative of 4x squared. So you get negative 8x. And then that negative 8x equals ma.
So energy is actually force?
Yeah, so Josh. Okay, I think we're okay with this now. This one works. Good discussion there. We'll go back to this. So here, if you know this, right? So if you take the derivative of this thing, right? Then that's the derivative of 4x squared. So you get negative 8x, right? And then this negative 8x equals ma.
Oh, negative.
So then you can just plug it in and get the acceleration.
Wait, does the negative matter?
Yeah, the negative matters. That's significant to that. I've seen other questions like this where.
So do you document you don't need it?
Yeah, because like. I mean, in this system or in a spring system, it makes sense because the force is like a restorative force, so it pushes you back towards equilibrium. So the amount of energy that you have, or the function that describes that energy, when you take the derivative of it, if you want to be able to figure out the acceleration is always pushing. It's like trying to push you back to equilibrium. So the negative is. Yeah, question, Jenny? Yeah, isn't this the problem where there's a point for units? They're super picky about units. You always have to use units. I mean, I've been taking points away from you all year because you didn't use units on quizzes. Remember, like, people who got the correct answer got a 9 instead of a 10? It equals this? Oh, just take the derivative of 4x squared, right? That's not the right notation. Okay, so that Elsa, that's how that works. Yeah.
Oh.
Alrighty. Now let's do the hard one.
Hooray!
We're dumb. I want it.
Yes, the one that I really do.
Yeah, but I just really want it. Like, it was sad about how we're seeing
Okay. All right. So this one, they give us these two crazy equations for. Oh, whoops! I'm still recording. There's going to be a giant movie. It's going to be the whole class period over again. Sorry. Anyways, this one they give us these two sort of crazy equations, and what's happening is they're saying that something has a charge of Q0, and it's within this radius of R. Okay, and then they're telling you that the electric potential is described by these two functions, and that's like one is inside and one is outside. Yes, does that make sense? This describes inside and this describes outside the sphere. Okay, so the question is, indicate the direction of the electric field and derive an expression for its magnitude. So how does electric field relate to electric potential? Yeah, there you go. So the electric field, I think, what was the equation say? dV over dr? Negative, okay. E is negative dV over dr. So all you have to do to get the electric field equation is take the derivative of these two things. It's not that bad, right? This is a constant, 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 constant. That's a constant. So basically, you're just taking the derivative of r squared.
Wait, so
that's
this is the
stupid.
derivative of r
This looks
squared?
really, really hard.
Right? And then this thing right here is a constant. So what do you do to it? That goes away, right? And then this is distributed. So that whole constant becomes out front 3q0 4 pi e0 r, and then this becomes 2r. So it's just 6q0r over 4 pi e0 r.
Oh,
See, it's not that hard.
that's horrible.
Really?
It looks
It's just
horrible, but it's
horrible.
not that hard. And then this one's even easier, right? Because what is this is just the same as saying q0 over 4 pi e0 r to the minus 1.
Yeah.
And so then that becomes negative q0 4 pi r to the r to the minus 2. Right? That's all. Okay, so let me go back. Okay, do you see that? Let me call this A because it's big and nasty. Do you see how that is negative 2a plus 3a times r over r pointing squared?
Oh, yeah.
Right? Now, what is the derivative of a constant? Nothing. Okay, because what is the slope of a constant value graph? 0. That's why you cross it out. Now let's just take the derivative of this, right? And then the all you do. This is essentially just so this is like 3a over r squared times r squared, right? So just take the derivative of that. What's the derivative of r squared? 2r. So this becomes 6a over r squared times r.
Oh.
Okay. Right, and then this one is just this one you're fine with, right? So this is the same thing. It's like a times r to the minus 1. Okay, cool. What's that? Yeah, you get it's like a r to the minus 1, so you get negative a r to the minus 2. Right. So when you do this, yeah, when you do this, if you think about these values, or if you look at the value of r, as this approaches, as little r approaches big R, then this graph comes out to be something. I mean, again, it's just like r squared, right? But because of this -2, it's shifted down like that. So it's not that much different from the graph in the last problem of the energy, right? But the issue here is this. It's all negative, right? This is all negative from the bottom. And if the voltage, if the electric potential is negative, right? How do you think of the electric field? No, that's not it. I had a cool way of showing this. And it's fun. Oh crap, what happened? It was cool, I swear. It was cool. Ah, okay, cool. So, if I show the E field and if I show the electric potential, right? So see, when I get closer to a negative, the electric potential is negative, right? So when you plug this in, when you get an electric potential that's negative, that means there must be negative charge in there. And negative charge means the electric field has to point inward. So I can choose, oops, I can choose that. Sure. Huh? That's gonna, yeah. So the whole sphere thing has a net of this. But we cannot escape the fact that the electric potential is negative inside this sphere. And if that's negative, there has to be a negative electric field. The electric field has to be pointing inward. You see why that is true, right? If I tell you that it's negative voltage in here, and this is why I did my handy dandy little thing here. Right? Why did I do this? To show you that when you well, I can't hide the charge, right? But if I show you a negative electric potential, that's the blue V. I'm using the voltmeter thing here to show you that that's a negative voltage. So wherever you have a negative electric potential, you have an electric field that points in. So as I go out, see, even out here, it's still negative. Boom, that's pointing in. So the whole point of that is just to say, okay, how do I know that it's pointing in radially? Because the electric potential is negative. And if the electric potential is negative, that means the electric field is pointing inward.
The electric potential is negative, so it's actually pointing inwards,
Yeah.
and then
And I specifically did this because I want you to think this way, right? Electric potential is negative. There must be a negative charge. And when there's a negative charge, that means there's an electric field pointing inward.
oh, so that's why it matters like whether little r is actually bigger,
Exactly.
smaller than big r, because
Okay? And then, when you look at this, right? When r is bigger than big R, or whatever, when the radius is bigger than r, there's no negative numbers. So this is constantly what? The electric potential is constantly positive, right? See, this is negative. It's negative for a while, and then it's positive later. But because of this negative, there must be electric field pointing inward. Now this one has to be positive. You can't make this negative. Because it has to be positive, then that must be radially outward. Because so what that means is we've got an M&M, right? And the candy-coated shell is positive. You see that? Because sorry. Exactly. The chocolatey center is negative. Like that's what this problem is doing. Okay, do you see why that is? Does that make sense? Okay, so we already did the derivatives, so that's fine. We can move on now.
so basically,
I'm sorry?
So basically, because you're deriving the like the equation you get in the velocity,
The electric potential, not velocity. It's a voltage.
voltage,
What I would say is this. If you look at that equation, when you plug in R for anything from 0 up, it's going to be negative. For example, look at this equation. If I plug in 0, what do I get? I get negative 2 times this gibberish. So that shows me that the electric potential at the center, at R0, at the center, is negative. So that means I have some negative voltage at the center. Right, the voltage, the electric potential is negative, some negative number. And because it's some negative number, that forces me to say the center of my sphere is negative. That means the electric field points inward. And then I'm just calculating. They told me to derive an expression of the magnitude of the electric field. So since I know that the electric field is the negative derivative of the electric potential, that's why I did that. The derivative did not tell me what the electric field did. I didn't do that first. Logic told me what was true about the inside. Now you could have just done the derivative and seen what happens.
And if I did the derivative and figure out what happens, then it would make it more obvious.
Yeah, I guess, this doesn't come out to be negative. I don't remember if it does or not. Do I have that solution thing here? Oh, crap, that sucks.
What's your homework tonight?
Okay,